Samuel Arbesman, Overcomplicated, Technology at the Limits of Comprehension. Embark on a journey into the world of overcomplication with Samuel Arbesman's Overcomplicated, Technology at the Limits of Comprehension. This book sheds light on the growing complexity of modern systems, from urban infrastructures to computer software, and how this complexity often surpasses human understanding. As the Age of Entanglement emerges, many people react with fear or reverence, often overlooking the middle path of honest reflection on the risks and benefits of complex technology. Prepare to delve into the differences between complicated and complex systems, the phenomenon of emergence, and the intricate dance of interconnectivity.
The rise of technological complexity. Glitchy software is frequently linked to incidents such as air traffic system outages and stock market crashes. The increasing complexity of modern systems, including urban infrastructures, website databases, and supply chains, has multiple potential failure modes. Complexity has reached a tipping point where it often outstrips designers' abilities to fully understand them. Contemporary computer systems' radical novelty makes them even more complex and difficult to comprehend than earlier systems. Our present technological achievements' trajectory and destination lie beyond human understanding and comprehension. The rise of technology ecosystems and interconnectivity resembles circulatory systems, where their interconnectedness is too fast, uncertain and complicated for human understanding. This overcomplication of technology elicits either reverence or fear among people. Those who revere technology are placing undue faith in its capabilities, whereas those who fear it experience maximum resistance towards automation and AI. The middle path of honest reflection about the risks and benefits of complex tech offers a balanced, optimistic mindset that sees the potential of untidy, imperfect systems if they don't become so complicated that they surpass human capacity to regulate them. The difference between complicated and complex systems. Complicated systems are not the same as complex ones. Complex systems show dynamic complexity and exhibit feedback, whereas complicated ones are only a tangled mess. Increasingly, technology's complexity mimics organic features, granting the benefits of automation. While people can reach a depth of understanding of a system through training, it is difficult for a single individual to grasp all the details, leading to overlooked aspects and occasional calamities. One common mistake is regarding technology as magical. It is critical to differentiate between complicated and complex systems for successful functioning. The Age of Entanglement. Computer scientist Danny Hillis identifies the early 21st century as the Age of Entanglement, where complex systems bring about unexpected phenomena. Abstraction is crucial in interacting with such systems, but it has limits. The volatile collision of hidden elements in a system causes unanticipated problems, like the 2010 financial flash crash. Experts can't control emergence, a phenomenon where interactions at one level lead to unforeseen results at another. The entanglement affects us all and requires nuanced thinking. Hillis encourages us to understand and adapt to the complexities of the modern world. The Internet's messy evolution. The Internet has become convoluted and complex due to the kludges, or makeshift solutions added over time to address its shortcomings. These fixes have led to bloating and the accumulation of outdated systems that continue to interact with newer technology. The result is a network that is far removed from its elegant and efficient origins envisioned by its creators in the 60s. The legacy systems run by institutions like the IRS are testament to the challenges of starting over. Ultimately, the Internet's evolution is a product of both accretion and interaction, a process that has made it a formidable but unwieldy beast. Interconnected system risks. In a world of massive interconnectivity, interoperability poses a growing threat of system failure. As designing for edge cases undermines simplicity, so do exceptions in language and programming lead to complex distribution. Modularity and system engineering hygiene can help limit complexity, but there remains a potential for a combinatorial explosion of factors beyond human comprehension. Such risks highlight the need to account for common rarities and their impact on interconnected systems. The ease with which seemingly disparate systems can now interact only increases the costs of failure, making continued attention to system design essential to avoid global disaster. The complexity of systems. In the book, the author explains how the limitations of human thinking hinder our understanding of complex machines and systems. The Therac-25 radiation machine serves as an example of how a software bug caused 6 patients to be overdosed with radiation. The designers failed to account for potential bugs in the software. Systems operate differently from human thinking, and machines count from 0 instead of 1. Humans become overwhelmed when processing vast amounts of data, particularly when stressed. Even in simple software programs, if-then statements branch into unfathomable pathways. Systems that optimize themselves produce useful insights, but nobody understands how. The author argues that bugs are not just annoyances to be fixed but also serve as a realization that we are in the entanglement. The era of specialization and new fields of study makes it necessary for teams of specialists to work on complex projects. While teams work well, no single person can grasp the project fully. Debugging and the complexity of technology. The complexity of technology creates unexpected bugs that often result from software developers' failure to understand their systems. Even systems designed to handle numerous eventualities may still fail when faced with unforeseen stimuli. Debugging software involves cataloging bugs and studying them like naturalists studying ecosystem phenomena. In the same way that cities accumulate complexity over time, machine learning algorithms may also seem like black boxes to developers. Innovative developers often purposefully test their system's durability using software like Netflix's Chaos Monkey. Finally, creators should cherish exceptions and rare instances as they contain crucial information that could help analogize technology to evolutionary biological systems. Embracing complexity in a new era. Mathematician Isaac Newton's unifying approach, seeking unifying principles, differs from English physician Nathaniel Fairfax's approach of observing and recording the diversity of natural phenomena. These two distinct outlooks show the difference between physics thinking and biological thinking. Complexity scientists generally build mathematical models that often result in deceptively simple, toy models, abstracted from the messiness of reality. Amid today's growing abundance of cases on the edge of technology, generalists and specialists find fresh purpose as they embrace the complexity in all its beautiful strangeness. With the emergence of technology systems that are too complex to be grasped by a single person, combining two approaches is fundamental to finding the right way to study complex systems. A modest but rigorous cataloging approach to technology, sorting things as a field biologist might, could serve better. Complex systems are analogous to biological systems in their complexity and interdependence, evolving over time until they fail. In conclusion, we are in a new era that requires us to embrace complexity with both physics thinking and biological thinking approaches. The Art of Understanding Technology. In his 12th century book, The Guide to the Perplexed, Moses Maimonides recognized human cognitive limits. During the scientific revolution, thinkers believed in overcoming incomprehension. However, today's technologies have generated new levels of complexity, which calls for humility. Our neurons are much slower than computer circuits, and our long-term memory can't store as much data as old Macintoshes. This creates a challenge in resolving bugs, as they may be too complex to comprehend. Tinkering with simulations fosters understanding, but neglecting technology's unknowns can leave you in the dark. Having a sense of wonder may provide a better perspective on technology's complexity, rather than seeing it as a mystery. Humility and wonderment will help you flourish in today's technological world. Understanding AI. The growth of AI has increased the complexity of technology, particularly deep learning and neural networks. The Defense Advanced Research Projects Agency aims to create explainable AI to help people trust it more. This is particularly important for self-driving cars and other technologies that challenge human trust. People from different generations are shifting their attitudes towards trusting machines, and rational approaches to technology are becoming more crucial as it becomes even more woven into society.
In conclusion, Overcomplicated highlights the current challenges and future prospects posed by increasingly complex and interconnected systems that often stretch beyond human comprehension. Despite this overcomplication, embracing a balanced perspective can bring to the fore an appreciation for both the potential and the limitations of these technological ecosystems. While the book acknowledges the growing complexity of technology, it also inspires optimism in the capacity to adapt, appreciate, and ultimately harness its benefits. It encourages readers to adopt an open-minded, inquisitive approach, fostering continuous learning and thoughtful engagement with the seemingly insurmountable entanglement of modern technology.